Hi. So we're going to continue this video right where we left off. So to recap, the last video we looked at the matmul+relu example, and basically we compared that against a bunch of different baselines, and all of these baselines perform much better than we expected. So they're all perform around 1 millisecond to 5 millisecond compared to our 800 millisecond number uh, with the naive MLIR lower, right? So the reason we kind of discussed in the last video was spectrization. But in this video and in the next few videos, I want to examine these baselines deeper. So I want to show you the code, I want to explore and kind of get to the bottom of things, of how these things optimize the same workload, right? So we have basically five baselines, which are listed here. So there is, so basically I'm classifying these under like with two axes, right? So on the left you have libraries which are mostly linear algebra focused. So these are all scientific computing libraries. On the right, we have deep learning or machine learning libraries. So that kind of differentiate these two aspects, right? And also I'm kind of can kind of split these in this kind of horizontal axis. So what I mean is these are libraries which are very big, very standard industrial grade. And these are comparatively speaking, smaller and probably easier to explore, right? So I'm differentiating this. The performance was pretty good in all of these cases, so it's not that much of a problem, but just to set the ground. Okay, so let's start with NumPy, probably the easiest one out of this. I don't really know what I'll talk about NumPy. I think it's very obvious. It's a fundamental package for scientific computing in Python. The core idea is you get these ND arrays and you operate on these ND arrays. You have a bunch of different operations that you can do, right? So let's go to the code. Again, I don't think there's much to show here. So in this folder, I have all of the different baselines. So I'll show them one by one. In this video, we'll only look at NumPy and pytorch. So for NumPy, let's start with this example code. If you notice why I've written this, I mean, this file is called numpy, not NumPy, because if you didn't start with importing NumPy, it leads to a circular import. So you can't just name your package the same as the thing that you're importing. Okay, so this code is a bit more than what you would think. So this is the basically you just create variables A and B where you are generally generating random numbers, and this we are sticking to the same size from the starting 256 cross 5 and 2, and then 5 and 2 cross 1 is 4, and we want to match these two and then do rel, right? So I have a warm function which just creates two random inputs and just runs the same function, right? And the idea is that we just want to basically warm up the system before we start, just in case there are some data structures being created or some other things that are being spawned, new threads being spawned, and we don't want that to impact our numbers, right? So we just run a warm up and then we do our actual run. So if you see here, we warm up the function, sorry, and then we then run the actual function, this time with timing, and then we print the timing. This is the timing I already showed you, but just for completeness, right? So let's just run this. It's as simple as this. There's nothing much to show here. It is instantaneous. I just printed out the result so that we can see that there's something coming out, and it's not like, in case some libraries might have lazy evaluation, and if you're not actually using the result, they may not compute it. So this is just a guard to ensure we're not against that. You have the actual number here, just 2.5 millisecond, like I said earlier, 2 to 6 millisecond. So this is it about NumPy, right? Ideally, I wanted to go into NumPy code and show you internals, but what I realized was Open Blast and it's a lot more difficult. Some of it is in Fortran, so I kind of didn't really do anything with NumPy. That's also the reason why we have these other libraries. They're also the same category of BLAS, basic linear algebra subroutines, and they are much easier to understand. So we will go deeper into those libraries. So for NumPy, this is it. So we are done, right? So now let's go to PyTorch and we'll spend a little bit more time with PyTorch. Now let's go to our example first, and then I'll come back to show you some differences. Again, I have a pytorch.py script. It's a bit longer, so I will again explain this a little bit. We have the same warm-up logic as before, right? So it's the same. Uh, I have no idea why my page down is misbehaving. I have to use my cursor. Okay, so we have the same logic as before, right? So we create two new tensors. So in NumPy, those are ND arrays. Here, the word is tensor. So we are saying that we want the same thing, right? 256 plus 512, 512 plus 1024. We are setting the device to be CPU. This is because I have a GPU on this machine and we don't want, let's not even go that, right? So we'll only run operations on CPU. And we set the D type to torch float 32. If you notice in NumPy, the default is actually float 64. So scientific computing usually requires more bits of precision, but deep learning gets away with lesser number of bits. That's why the standard things in deep learning is like 16 bits and then further quantization down to 8 bits and things like FP8 and so on, right? But today we're just looking at the default. We don't care about exact numerical accuracy between this version and that version. We just care about time. So this is float 32 standard, right? And we do the same warm up and we have the same function, same logic. So you see here is the core uh, you see here the core logic here where we are doing the matmul followed by the relu, right? So this is the syntax. A at B is the matmul and torch.relu is the operation to do relu, right? This looks a bit different from the numpy version. So if I go back here, if you see the core logic happens in these lines, the matmul looks similar. The relu, instead of relu, we have np.maximum. It's the same logic. If you understand relu, it's just 0 before negative, and after the positive portion, it's the input. So it's just a function like this. So this is the same functionally the same thing that's happening here. But this also goes back to show you PyTorch's structure of it being a deep learning library, or sorry, machine learning library. You have uh, you have these operations that are needed for neural networks built in, right? So that's why it's easier or it's straightforward. So this way of running this function of, I have no idea what's happening with my arrow keys. Really sorry about that. So this up to this, whatever you're seeing here, this way of running this function is what you normally do in PyTorch. It's like what you normally do from a Python console also. I could just open Python console and I could run these commands. This is what is known as eager mode or the default mode. That is what you do normally, right? There is also something called torch compile, which I will go into more details momentarily. So there is code here to basically do the same thing with torch compile, the same logic here with warm up and running. But the point is, like even without compile, eager is like, you think of it the default more direct comparison. Compile is going to be faster, it's going to be much faster, understandably. Though it's actually meant for GPU and A accelerators, but even on a CPU is going to be faster. So it's not may not be a fair comparison, right? Eager is a much more fairer comparison. So let's just run it just for your it's just the numbers are going to be same, but just to show you. So you see again tensors being printed out. It's going to be 256 cross 1024, and it's taken 1.1 millisecond to run that part. Now it's actually running the compile part, and you see here it's taking a lot longer. I'll talk about that later. But the final version after the warm up, the final version is 0.7 milliseconds, faster than eager. So that's it. So now you might have a question. What is the benefit of using PyTorch? Because in this situation, NumPy and PyTorch are very similar. They've done the same things. You have matmul, relu, on CPU. So I just have a quick slide to lay this ground in case you're not clear or you're not aware about this. So the point is the way we use PyTorch today, especially in eager, is like the most basic version, right? At that, if you're going to do that, you might as well use NumPy. PyTorch is giving you a lot more, which we are not using here in this example, but I want to call out those things, right? So the first thing is that it basically allows you to run on multiple devices. So on NumPy, you can only run on CPU. In PyTorch, you can actually run not on CPU, also on GPU, not just GPUs, different AI accelerators from different companies, different architectures. So all of that is abstracted away. You can just change one line, which is device from CPU to GPU, and the whole thing will work. And the second thing is I mentioned this a little bit earlier about D types. So you have option of multiple D types, like not just 432, 416, B416, and so on. They have different trade-offs in terms of speed and computation and accuracies. But you have that option, and it's very easy to use. Just change one thing, and PyTorch will take care of running the different code, underlying code bases to do that operation, right? And finally, the core thing that PyTorch brings to the table is autograd, basically backward passes, which means easily being able to train neural networks, right? We are not doing that. In this example, we're just doing matmul+relu, right? That is what you call a forward pass or like an inference scenario. But realistically, when you're building models, you also have to train the models. So you have a backward pass and there's a lot of work. And that, all of which is PyTorch is going to abstract away and give it to you automatically, right? Because we didn't use any of that, numpy and pytorch are very similar in this scenario. That is usually not the case because you need all of these extra features from pytorch. Okay. So let's go back to my code, and I want to show you a little bit more detail about torch compile. So I pulled up a few tabs. So this is the home page of pytorch. Nothing much useful here. Um, this is the intro page for torch compile. It is not very clear. It's a very advanced document. You need to take time. Similarly, I pulled up the paper of PyTorch 2. This is also PyTorch 2. This is also a very advanced document. You need to go through the paper to understand the details. There are no clean diagrams. Instead, I'll show you this diagram. Maybe this is an easier step. Like you can look at this link. It's a much more gentler introduction to Torch Compile. But the point is, Torch Compile has multiple components, but the idea is it takes in your user program within code, and then it's going to compile from that Python code where anything can happen because Python is just in time. Python is it's there's an interpreter, right? So it's not compiled, it's interpreted. So you can do whatever you want in Python. Things can change dynamically. But given a user code in Python, this whole stack will convert that code into a lower level, more advanced implementation. So in this case, the backends, for example, they talk about Triton here. Triton is for meant for GPUs. C++ OpenMP, that's meant for CPUs. That's what we'll see today. That's what we'll be using. We are using in our case when we run the Torch compile. And you can have other backends, and there is a lot more things here. But the idea is that you can actually reduce the overhead of moving control between your CPU and your your host and your accelerator. Of course, in our example, everything is on the host, everything's on CPU, right? So the logic is not very clear. But for a device, for an external accelerator like GPUs, you move your control flow between your device host and your device, and that leads to more overheads. Idea is to capture everything that you want to do and then simply kick it off with one compiled artifact on the device. So this blog has a lot more details and it's worth looking into it, but I'm not going to go into this. I'm just going to show you, in our case, with our code, some of this, a little hint of what's happening, right? So the first thing I'll do is I will open the code, and what we'll do is we will basically, let's say, remove this warm-up, right? So we want to not have a warm-up. We're going to like directly like run compile. So basically on this line, we say we want to compile this function. This function is a normal Python function, right? This function is the one that is doing a matmul+relu. So this is the function. And then we are saying we want to compile the function. And then instead of warming up, we're just going to like run it directly, right? And when I do this, I'm going to run, let's run this again. So it's going to, I mean, obviously it's going to run eager first, 1 second, and we wait for the compiled version to run. We wait, we wait. Okay, that's taking a lot of time. You see here, it has basically taken 10 seconds, right? That is crazy amount of time. Understandable, right? Because the point is compile is more complicated. It's doing more things uh, in a bid to come up with an optimized version. And it is only worth it if you're going to use an optimized version again and again and again. So which kind of happens in the case of normal deep learning inference scenarios, because you're just going to run through that thing for the next token, for the next token, and for the next request and so on, right? In our case, we have a single matmul+relu and then we call it once and then we're done. We are not actually using it again and again. But the point is you spend 10 seconds in compiling that function once, and most likely, assuming that shapes don't change, there's some caveats there, you can just basically reuse that compiled artifact, and that's the faster version, right? Now you might also have one question here, because if you see in this code, the compile line happens here and then the run happens here. So you might ask like, why did that happen? And that's because compile is actually like just in time. So it's not, though it says source compile here, it's not actually compiling it here. It compiles it later when you actually call it. And then it takes the actual shapes of that you're passing in. In our case, it's 256, 512, 512, 1024. And it'll basically have to recompile if the shape changes or if it's not compiled for that shape. So in this case, if I give another two inputs which are with different shape, it's going to take, again, it's going to take some time to compile. I mean, I don't know if it'll take 10 seconds, but it'll take a lot more than that 1 millisecond that we saw to get to that state. Okay, now I will show you some of these compile artifacts because that was the aim of us coming to actually running this to try to understand what's going on behind the scenes, right? So we can see both the compiled and the eager version. So I will show you maybe I'll show you the eager version first. If it is yes, okay. So in the pytorch repo, the repo is very big. It can become very confusing to navigate. So this, I don't know if this will help you. So the point is there is an A10 top level folder which is there for A10 tensor related stuff. So there is this. This is all C++ code. This A10. This is the core engine behind pytorch, right? So you use it in Python, but the backend is in C++. And this A10 subfolder as the all the logic for these tensor operations and so on. So, I mean, if you go there, you will see a bunch of different backends. So these are other backends, right? We are like thinking about CPU, but there are other backends. So CUDA is NVIDIA GPU, and you have AMD GPU, you have Mac um, backends, and all of this, right? You'll have Intel somewhere, and all of this. Now, the point is, the thing I wanted to show you was basically native. So the native ops, where is the native folder? And you have some of the operations implementations in these folders. So for example, in CUDA folder, you'll actually have CUDA kernels do different things like activation. Relu should be somewhere here. Like, okay, let's just see activation leaky relu because I just came across it. So this is going to be like the actual code that will run when you call relu, in this case, like leaky relu. And you'll see here it's going to point to something. It's this is basically the code on the host, and somewhere there is going to actually point to your um, kernel, right? The kernel is not here in this case, or it's a bit of a more complex example. Maybe if I open something which hopefully has a kernel inline, that would be nice. For example, I'm just seeing if we see, okay, there we go. So um, this is possibly one of the kernels. I don't know, I'm not able to see this clearly here. Yeah, so these are some kernels, right? Of course, I mean, you can go take a look at this later. We are not worried about CUDA today. In this set of videos, we are worried about CPU. So let's like completely leave that. Let's come back to CPU. So these are the CPU ops implemented, the CPU backend in eager mode, the default one. So you have a bunch of functions here. I like open activation, and let's see if so we have different activations here. We have lock sigmoid. All of this is just normal CPU code, right? Like C++ code. And you see here actually it uses something called vectorized, and this is actually linking back to our vector library. Like there is implementation in PyTorch wrapping. I'll show you that in a moment. I'm just saying log sigmoid. See, they also have the backward kernels to do your training. We have threshold, continue backward. Okay, I don't know if I want to find relu in this huge file, but you get the idea, right? So the logic that we are looking for is implemented here, even in the case of CPU, and it uses something called vectorized, and that is basically a sub module in PyTorch. I have it open here. So this is basically in A10 CPU vector. So here we basically see them pointing to the intrinsics. So you see this, you are able to identify this now. Vectorization 512, if I open this, there's going to be a bunch of header files which wrap the underlying intrinsic function. So you can see this. These are the vector intrinsics, and this is they're going to have wrappers for every flavor, right? So because you don't know if that machine has uh, 512 or if it only has AVX or AVX2, so you have to do neon is yet another such SIMD intrinsic. So you have to basically they have done this hard job of wrapping and providing all of these lower level functions so that you can call the relevant one from your code, right? So this is what is happening, right? This it's going to this vectorized version, which is why it's actually very fast. Of course, because there is still a gap between what we are running and what we're seeing. When we run here, you don't really get to see You don't get to see a binary. It's in Python. You don't get to see the intrinsics in action, so it's not very satisfying. That is again why I have brought in these other libraries where we can actually go closer to the code and we actually see it. We actually have the binaries. So we'll do that in our future videos. But for the moment, you can imagine that there is a link between this and this is where it comes to actually run the code, and eventually it's going to run the vectorized version, and that's why it's fast. Okay. Now I want to show you finally, basically we're done with eager. So I want to show you a little bit, spend a little bit time on compile. In compile, so the first thing you can do is basically you can look at every time you run compile, you basically get a bunch of relevant files in the stem torch inductor something, right? So it adds your username, but torch inductor is the thing you need to look for. So if you just run the code, you're going to have this folder. So you see here, there's a bunch of intermediate files that is created. So I'm going to like remove this just to show you that uh, it's created when you run this thing, right? So let's run our version again. Of course, eager will not create anything. So at this point, if you go and check, there will be nothing there. When you get to compile, you will get those intermediate files. Let's see that. 10 seconds. We need to wait for 10 seconds, maybe more. I think it's taking a lot more than 10 seconds this time. Okay, 21 seconds. Fine, whatever, right? So this is like, if you're going to use it only once, then obviously compile doesn't make sense, but ours is a toy setup. So that's how it is. Okay, so let's go to torch connector. So this folder is got created again. There's a bunch of files. The names will change, the numbers will change because they are like code generated files. So I just run tree to show you this folder. There's a lot of stuff here, right? And it's not easy to directly link. So I was going through this earlier. It's not very easy to link this to the exact code that we ran, unfortunately. Things are much more cleaner when you run on GPU. So you get right on kernels and there's not this much of output. But I'll give you some clues and we'll explore a little bit here, right? So the first thing you need to know is you need to search for a Python file. So you see there's a bunch of CPP files. That's all fine. But you need to search for a Python file. So there's one here, right? So this Python file is the entry point in inductor to the lower level code gen portion. So you can kind of understand the flow by looking at this file. If you have to look at only one file, look at this file, right? So in this case, it's KS. So these are generated things. So you don't really know. So this is the thing you need to look at. So this is what inductor, which is the backend of torch compile, generates, right? And if I just go back to this diagram in case that helps you follow through again, once again. So in torch compile, we have many components, but loosely you can think of it as two main components. There is a front end and there is a back end. So the front end is what is called dynamo. We don't really see it. It happens inside. The back end is what is called inductor. And the inductor is the one that is going to generate code for your actual device, right? So here we see this inductor generated file. This is a Python file which you can rerun. So that's the idea. But this file is actually capturing your compiled uh, task, right? The task that we have. So if I'm just going to go to scroll down and show you the like relevant code, right? So you'll always have this. You'll always have a runner and you'll always have a call. So that's where you can directly like go and see what's going on. And this is the exact translation of what we wanted out there. So basically it says that we have these args 0, 1 and 1, 1, which are R matrices, input matrices, 256, 512, 512, 1024. And then it's actually going to do the matmul and the relu, right? That's what we have to do. So if you see here, actually it's calling external kernels.mm. So it's generated this code and it's decided to use something called external kernels. We'll see that in a moment. And then it's then doing the relu, right? And it's calling another function, and you can see if you follow the function up here, you will see that this is the relu function. So I mean, just take a look at this. So this is where we're actually getting into your optimized for your CPU code, right? One thing to mind, fused, it's not really fused, right? The name is confusing. It does not, though it can, and it does in many occasions, fuse related operations. So basically you can fuse an operation A and operation B, which are next to each other, into one kernel. In this case, it has not done it. The name is misleading because you see here, this is only to the relu path. And if you see the code, you see we are using OpenMP. So basically it is generating code which can actually use all the threads on my machine. It has somehow come up with the number 8. It's figured that out. So it is written code, C++ code, making maximum use of your hardware. And on top of that, it's doing some checks and so on, but the core thing is here again, right? And you see here it's loading from the input pointer the data, and then it's calling AT, which is a tensor vector clampment. So this is the actual ReLU logic that is happening, and then it's storing the results back, right? So you see here clearly there is only ReLU. There is no matmul here. There's only ReLU, and this clampmin. If you go follow this function, you'll be able to find the code. And again, this is under vector namespace, which means this is also vectorized version. So it's basically doing both vectorization and multi-threading to get maximum out of my CPU, right? Okay. And you see here this other thing which is a bit opaque and unclear, because you see it just says external kernel, external kernels.mm, and it's importing. So I was trying to follow that along, and it was a bit of a circular thing. I didn't have complete clarity. This is much more clear in case of GPU, and maybe in a future video I'll show you how it generates Triton backend code. That's much easier, especially for things like matmul. But these external kernels, you see, you can follow through to this torch induct kernel folder, where it has some of this code for the external kernel logic, right? So basically it's doing some work, including things like auto tuning. So basically it can figure out what is the best tile size. So in our case it's 256 plus 512, right? But you might be able to launch kernel which is smaller than that and then run it again and again. And this is true even more for Python. You see here there's a bunch of different Python templates for different, like for different hardware, for different categories and stuff like this. And it has auto tuning capability to go try out different combinations and then come up with the best performing one, which it will then compile and use for your future, right? So this is where those 10 and 20 seconds that we saw earlier is going to. It's doing all this extra work, right? So it's not very satisfying to, like, because you don't see the kernel here, right? But unfortunately, that is the case. I'll open some of the other files and we get a little bit of a clue of the link to vectorization. So let's just go line, I mean, file by file, right, and see what's there. This file is basically the same as, it is just a generated version of this ReLU kernel. So you see the same ReLU kernel logic that is happening. So it's not really about matmul, but okay, that's fine. Let's open the next one. So I'm just going to go show some of this. I cannot explain all of this because there is a gap, right? We don't really know the exact flow of logic in PyTorch. When it comes back to this, we can do some more code exploration to find that out, but we get hints, right? And that's what this series is about. I just want to give you a taste. We don't have the time or the uh, efforts here to go in all that. So this is again similar function. You see here it's actually checking your CPU capability for AVX512, AVX2, and so on. You see this? So that's your link to vectorization again. Let's open the next one. What is this? See, this is interesting. So this is, you'll be able to recognize this from the last video. So it's trying to literally call an intrinsic. It is just wrapping an underlying intrinsic with a new one. So I was curious what this is, because I'm looking at this and I'm like, why is this coming, right? There is BF16 here. Our data type is FP32. We have never gone to BF16. So I really cannot explain why it's needs this, right? Is this for something else? Is this used part of the doing auto tune? I'm not sure. But I was curious to understand what this was. But luckily we have our reference link. So basically we can just go here and search. And the thing we want is CVTNE. These things have weird names. So this thing, of course, this is a 128-bit version. Here we have an 512 version, but I don't think structurally it would matter. But okay, let's just open one of this. And you see here, it's talking about this instruction being available on AVX 512 BF16. If you remember in the last video I showed you, my CPU does have this. And what it's doing is it's converting packed single precision floating point elements into vectors to packed BF16 floating point elements. So basically this is a vector version. So this must be convert, right? So it's a vector version of this conversion, because you have to change your logic, right? You're going from 32 bits to 16 bits. You have to like drop something. You have to do that approximation. But this is a vector version of it. So you're actually taking those 32 into 512, right? So that's like, what is it? 4, 8, 16. 16, you're taking 16 different elements and you're doing all of that in like one shot, right? So you're basically converting full vector of 32 bits to 16 bits. So that's the use, but I still can't explain why we need this in this particular example that we're using. So I don't know. But let's just keep looking at other files. So we have 6s, and what is this? It's more of the same code. We saw that. Let's look at OJ. This is yet one more chunk of this, the very same function. I don't know if this is from two runs because there should ideally be only one run. Because we removed the warm up. We only have warm up. We don't have another run. So I don't know what that exactly is. Uh, this is yet again the same thing. So I think this is definitely two runs. Maybe it was auto tune and auto tune created two runs. Yes, okay. This is the other thing I want to show you. So this is the only clue I got towards our matmul. So you see here again intrinsic. It has two variants. There is a 256-bit variant and then the 512 variant, but otherwise exactly the same. And you see here this function. This is dpbust. Let's go and put this. I'm looking for a version without mask. Hopefully 512 and EPI 32 is fine. This one, right? Yeah. And you see here it needs VNNI, which is that vector neural network. Vector neural network instruction, if I'm right. And you see here in the description, it says multiply groups of four adjacent pairs with corresponding integers, and then sum these with the corresponding 32-bit integers. So basically, this is an actual neural network focused instruction. It's That's why it comes under VNNI. It's multiply and accumulate in one instruction, full vector, right? So basically, you have matmul also. So that's the multiply and add kind of thing. It's getting closer to your okay. It's not really matmul, but it's getting closer to your matmul, right? And this is we see that this is referenced here, but again I don't know how it's used because that link is not exactly there. Okay, so before we end this video, I will just show you one last thing. So there are a number of ways to get more logs out of torch compile. So in this case, there is a torch logs, basically the torch logs variable, and you can set various things. So I'm just going to run with inductor. You can instead set to dynamo, set to guards, and get other aspects of torch compile. But this can be a good clue if you want to explore this further, because this can give you a little bit of idea of what it's going through, right? So basically, you see here it's registering a bunch of templates for matmul, for different devices also, for whatever it's worth. Let's see, it's running. Where is it running? There is a FX graph cache hit. So this means that the last run is alive, is there. We have those files in the folder. So it didn't actually have to compile all of that again, right? So that's why there is a cache hit. And that's why it's missing some logs that I was expecting to see. So let's do one thing. Let us just remove the cache and let's run this again. Mhm. This is what I actually wanted to show you. So there is now cache miss, which means it has to compile. So this is where it's actually going through compilation for our scenario. And you see here 18.mm showing up. That's our core matmul. So there is this kernel.mm.py which tries to tune this 810mm. And see, this is the input default size that we pass in, right? That's the default. So I don't know, it starts from there. And we have some interesting things here which I have not fully explored. And maybe we'll do this again in a future video where it's actually talking about how to organize your nodes in the FX graph in the inductor, back basically the how do you organize your ops for other objectives, which is like for peak memory. So it seems to be trying out different algorithms to try to minimize peak memory. So that's again something interesting we can explore. But the idea is finally it runs, it actually compiles this time, and it kind of gives us a clue of what files to look at. So inductor kernel mm.py, right? So I was in the kernel folder. There is this mm.py, and here you have a lot of this code is of course for Python for GPUs. I mean, there's not that much work I mean, CPUs are not that much important for PyTorch, right? Obviously, but the code is here, right? The code that we will need to find out is here. But of course, this is very interesting to see, and I will have future videos, separate track, maybe separate playlist where we explore the Triton plus compile angle, and maybe we'll come back to these things. But the external kernel choice, this line is where it kind of decides to do the torch mm for this particular CPU op. I saw it in the log somewhere, and it basically goes through that auto tune function. So this is the logic here. Okay, so to recap, we basically looked at code of basically what code runs to run examples in numpy and pytorch. We saw the performance less than 10 milliseconds, less than 5 milliseconds. In fact, we saw that they use, at least we saw that pytorch uses both multi-threading and vectorization, and some of little bit of the code of how it does that. We didn't go into details in numpy, but we will look at other blast libraries in the future in the next video. So maybe that will be clear that part up. In PyTorch, we also saw, apart from eager, the compile mode, which makes things even more efficient, the cost of one-time compile. But you see here that in this approach, you have somebody has done extra work. I mean, in case of NumPy, it's hard-coded templates, but even in the case of PyTorch, there is functions and wrappers for vectorization, and but also this auto tune and the concept of being able to compile different angles and try to optimize and try out different things. So when I started exploring MLIR, that is exactly what I wanted to go at. I wanted to be able to run my MLIR program on CPU and tune and get better performance. But where I am stuck in is basically actually comparing and like fusing the different kind of optimizations. You have tiling, you have fusion, all of that, but you also have vectorization. And how do you do both of that ideally automatically, right? That is what I wanted to solve with this playlist. But so far, I haven't done it. I've tried a number of different things. I haven't succeeded. Let's see. Let's see how it goes in the future. See you in the next video where we will go deeper into the other libraries, and that is also very interesting. So I'm also looking forward to that. See you.